We're going to begin the meeting with a short briefing on how to use the Q&A from Lindsay Smith. So over to you, Lindsay.
Sorry, apologies. Justina, can you reshare there? I wasn't able to unmute while I had your screen on.
Not to worry, these things happen.
Okay. There we are. Okay, thanks everyone. Welcome to the 2021 edition of the GIF meeting. I'm just going to go through really briefly how to use Slido, which is one of the tools we'll be using to ask questions in today's meeting. So if you've attended a GA4GH meeting before, you probably know how to use Slido, but if you haven't, you can navigate to slide.do in your web browser. You can also use your phone if you wish to take a picture of the QR code that's on the right-hand side there. There's also an app if you prefer to do that as well. But once you're on Slido, you can enter the event code #GHIF, and that will take you into Slido. There will be a section to type in your question. You can do so anonymously or type your name in as well. And once there are questions up within the Slido, you can upvote other questions. So this will help us manage asking the most popular questions first. So what I'm going to do is we're going to ask a couple of questions off the top here to get you familiar with Slido. So I'll wait a minute here while everyone navigates over to Slido, and we'll get started with some of those questions. So Justina, do you want to head over to the next slide while everyone there we go. So our first question is, what organization / initiative do you belong to? So again, you can either copy the QR code or go to slido.com and enter the code GIF, and you should see this question pop up right on your screen, and you can type in your answer. All right, lots of Australian Genomics, NHS, DNV, Genomics Laboratory Hub, German Human Genome Archive, India, awesome, welcome. Elixir Hub, Oslo University Hospital, welcome everyone. Children's Hospital, Eastern Ontario. Awesome, I'm seeing quite a range of all over the world here. This is awesome, thank you for joining. More Australian Genomics, Genomics England. Wonderful. We've got 35 answers in so far. If anyone is having any issues navigating to Slido, just please let us know in the chat and we can help you out. Brazilian Initiative of Precision Medicine. Cape Town, awesome. Great, okay. So it looks like everyone's getting the hang of it. Justina, do you want to head over to the next question? Okay, so what is the area of focus of your initiative or institution? So rare disease, cancer, complex, infectious disease. And this question should again just appear right up on your Slido screen. Okay, lots in rare disease. Rare disease still taking the lead here. Lots of infrastructure development as well. That's great to see. Oh, 41 answers in, that's great. Okay, more infrastructure development. Interesting. Okay, great, thanks. And next question, Justina. And so the next question is, which GA4GH standards or policies have you implemented, if any? And this will also help us with future meeting content in terms of things people might want to present or hear about. So there should be, I think, a multiple choice option there, or to type in. Just get Duo, Phenopackets, Beacon, none yet. Duoverse, another beacon, return of research results. Cram for each duo beacon, awesome, a couple there. None yet. That's all right, hopefully we will interest you in a few today. Duo beacon, machine readable consent, awesome. Another consent. Beacon, Matchmaker Exchange. So Matchmaker Exchange is one of our driver projects, so not a standard. That's right. Phenopackets Pedigree Duo Beacon, awesome. Great. And Justine, I think we've got one more question here, just to get everyone here. Yep. So here's another one. Please list any data types your initiative is currently collecting or have collected. So we have a bunch of different categories here: whole genome sequencing. You know, are you looking at gene expression panels, any type of clinical data, phenotype data, imaging? Let's see. Lots of whole genome. Oh, it's not multiple choice. Oh no, that's all right. I suppose whatever one you're collecting the most of. Okay, so still lots of whole genome and whole exome sequencing. All right, so hopefully everyone is now familiar with Slido. They have it up on your screen. So we will be using this. So as presenters are speaking, you can ask questions in the Slido at any time, and then we'll get to them at the end of the presentations. Okay, and then I think that was the last question, so I'll be handing it back to Catherine to walk us through the introduction.
So good evening, good morning, wherever you are. I'm going to just take over the screen. Yes, and welcome to this meeting of the Genomics and Health Implementation Forum. This is the second one that we've had, or the third one that we've had virtually. We're really looking forward to getting together in person next year. So the goal of GIF is to bring together large genomic initiatives, particularly initiatives at a country or a national level, and with a focus on the implementation and contributing to the development of global alliance standards. In addition, though, we've found that GIF is a great forum for sharing best practices. We all come up with up against the same challenges in the implementation of genomics into clinical practice. So it's also a great forum to share resources, expertise, experience across a whole range of issues in addition to global alliance standards. Now, global alliance standards really span around this entire circle from the data donor, the patient, or the volunteer. And we have standards that apply to consents, to sequencing, to ethical standards and data security, really then into how we're reusing that genomic data either as clinicians or as researchers to help us analyze genomics data. Now, the structure of the Global Alliance is around these technical work streams on the left, as well as the foundational work streams across regulatory and ethics and data security. But what we've found is most important in the development of standards is the engagement with what's happening in the real world, i.e. us who are within different initiatives that are looking at the implementation of genomics, whether for research or for clinical care. And initially, and to this day, we have a series of drive projects across a whole different range of areas, and including some national initiatives such as Genomics England, All of Us, Australian Genomics, GEM Japan, H3 Africa, that's a continent. But what the goal of this engagement is that in the real world, we can identify gaps where we need to develop or apply standards and contribute to their development, so that there is a constant interchange between the input from the driver projects, identifying needs, but also then being able to test the standards as they're in different stages of development. Now, We initially started by bringing countries together then because we needed to particularly find a scalable way. You can't have every country as a driver project. So the national initiatives coming together arose because of the need to find a scalable mechanism for incorporating many voices around the globe into the Global Alliance for Genomics and Health in terms of identifying areas of need and helping to adopt standards so that we're all speaking the same language. It's also, we need to make sure that our standards are fitting the needs across multiple different initiatives and particularly across multiple different models of healthcare systems comparing, say, Genomics England, which has the centralised system with the NHS, to a place like Australia or Canada, where we tend to have states and provinces and a federated approach to our health system. One great thing around the national initiatives, and we could see in that the initial poll that we did today, is we really are touching around the globe, and this is a place where we eventually hope to have all 192, I think, countries represented. We're currently sitting in the high 30s. And this is also a mechanism to bring together the users of genomic standards, the people on the coalface in clinical research setting, with all the brilliant minds that are working across the work streams of the Global Alliance. So a bit of history, we started off back in 2016, bringing people together in Vancouver and Canada. And originally these meetings were more show and tell about what we were starting to do or we were thinking about doing. But what's been great is over the last couple of years, as many of our national initiatives are reaching a maturity and implementation stage, that we're now able to share practices around implementation of standards and the use of genomics, as well as doing pilot projects around data sharing across national borders. So we formalised GIF as the Genomics and Health Implementation Forum and as the implementation arm of the Global Alliance in 2020. And unfortunately, since then, we've been virtual because of you know what. So here we have current members with a great representation, but we really encourage you to join up with GIF. We also provide resources on the internet across not just the application and how to implement the Global Alliance standards and the links into the Global Alliance toolkit, but we're also sharing a whole range of different resources that have been produced across different initiatives. For example, such as minimal clinical data sets, which is the optimal collection of clinical data for a specific clinical issue that is helpful in terms of the interpretation and prioritization of variants within a genome. We're also sharing across a whole different range of consent clauses and consent tools. We have access to evidence that's out there from a health economic perspective, which is really useful, again, bringing experience of other countries as we're advocating to our own governments in terms of what we want to implement in genomics practice. There are technical and data tools. There's even examples of media publications and also how we respond to different calls for information about genomics or challenges or response to data breaches. So that toolkit is growing and is also freely accessible, but we also encourage people to contribute to it. So like American Express, membership of GIF has its advantages. It's a really great global community and we can contribute to standards, but there's a whole range of tools and resources that are freely available to members of GIF. So how do you become a GIF member? If you go into the implementation tab on the Global Alliance website, there's a very simple and easy short form to you to fill out and to give a bit of information about your initiative. And in addition, we're certainly been doing it virtually, but we've been increasing the resources and the contacts we have across the GIF community. We have a monthly newsletter and we've identified a whole range of different issues that have common interests. We're going to hear about some of those today, for example, around gene curation, around clinical data exchange, regulatory and ethics, consent, and how to approach end-to-end implementation of standards. And so each month we have a newsletter that really highlights and does a deep dive on each of these topics, as well as looks at examples across the different initiatives of the membership of GIF. So with that introduction, let's jump into today's meeting. And we're going to start off today. We have two 2-hour sessions today and tomorrow. Today, we're going to be approaching gene curation, approaches to data storage, clinical data exchange, and pathways to optimizing genomics in healthcare. And then tomorrow, at the same time, we also have a really interesting program focused on regulatory and ethics, quality control, and then exemplars across different initiatives of the end-to-end implementation of Global Alliance standards, and a demo of the global GA4GH starter kit. So we encourage you to participate. We've all practiced with Slido. It's fun. If you want to make a verbal question or comment, you can raise your hand, but it really, using Slido probably makes it easier for everyone. And we're going through now, and we're going to start with the gene curation session. And we have two presenters, and then we'll have time after Zenitsa and Marina present. We'll have time for questions at the end of that particular session. So I'm going to hand over, first of all, and hand over control of the mouse to Zenitsa Stark. And Zenitsa Stark is from Australian Genomics and is going to talk to us about sharing gene curation efforts and highlight wonderful collaboration around PanelApp and how you can bring PanelApp to your national initiative. So over to you, Zenitsa.
Thank you, Catherine. I'm going to present the results of a pilot project that we've been working on with Genomics England over the past 3 years that has improved the quality of our gene and virtual panel curation using a common platform called PanelApp. So why are we talking about gene curation? I think everyone's much more familiar with the concept of variant curation and understands the importance of carefully gathering evidence and appraising it critically before we decide that a specific variant causes disease. Well, gene curation is the same, except it's all about the relationships between genes and diseases. A good understanding of these relationships is actually really important because it underpins the way we set up analyses, particularly of genomic data in rare disease patients and families. It helps us interpret variants accurately and also helps us to reach appropriate conclusions when it comes to case level interpretation. This is obviously a very important area, but there's wide variability in practice. We're also much more familiar with the challenges presented by variants of uncertain significance, but certainly the whole area gets a whole lot messier if we also throw into the mix genes of uncertain significance or GUSes, or even mechanisms of uncertain significance or MUSes. So clearly we need standards, but we also need the tools to share existing gene curations and to try and harmonize them to promote best practice. So we have been contributing towards the international effort in gene curation through an open platform called PanelApp. Many of you will be familiar with PanelApp. It was originally developed by Genomics England for use in the 100,000 Genomes project, and now also contains virtual gene panels curated for use by the NHS Genomic Medicine Service. Genomics England very kindly made the code for this open source and helped us set up our own instance at the end of 2019. Our instance is called PanelApp Australia and brings together virtual gene panels that were curated by translational projects in Australia, in particular those used by Australian Genomics and Melbourne Genomics, and now also increasingly supports virtual gene panels curated by diagnostic laboratories. So we've used the platform nationally to build a consensus and improve diagnostic practice within Australia. But having a common platform that we share with Genomics England has actually allowed us also to share the gene curation effort between the two countries. So now we basically apply the same rules when it comes to gene disease validity assessments. So the platform uses a very simple set of rules based on a traffic light system. So green genes are those that have a high level of evidence for association with disease. So variants in those genes would be reported in diagnostic practice. Amber genes are those that have a moderate level of evidence, and red genes are those that have a low level of evidence or are disputed or refuted. In addition to applying the same rules, we're now also capturing data in the same format. So not just the assertions that we make for specific genes, but also, for example, the modes of inheritance, recording the supporting publications, and obviously recording the disease against which the assertion is made. We have made the choice to retain separate governance, and basically that allows us, for example, to have a slightly different repertoire when it comes to our virtual panels. And also, if we don't reach agreement with Genomics England, we can maintain our own rating for a specific gene disease association. Having this common platform has made it very easy for us to identify and resolve discrepant gene disease associations. So basically, we're able to download any panel that we like from one instance and readily import it into the other. The tool has compare panels functionality, and on the left hand side here, we have a snapshot of the mitochondrial diseases panel, and with the two panels, the Australian one and the UK one, laid side by side. So we can very easily identify, for example, genes that are present on one panel but absent on the other, or genes that have discordant ratings. And then we can go to that pair, review the evidence, and try and reach agreement. So over a period of 15 months, we systematically compared the content of 80 diagnostic rare disease panels between the two countries. 3 of those panels had completely concordant content, but 77 didn't. And within those 77 panels, we identified over 2,000 discordant gene disease pairs, which is obviously a concerningly high number. So we've worked through each one of those discordances and exchanged reviews to try and reach agreement. And you can see what's happened here with the intellectual disabilities panel. We identified over 300 discordances, which we reviewed, and now the two panels are much better aligned and are concordant in over 85% of the content, which is very pleasing. So this has been a huge improvement in the quality of the panel and the evidence base that we use for diagnostic reporting. In addition to comparing existing gene curations within our systems, we've also put a huge amount of effort into curating new gene disease relationships. So obviously, new gene discoveries are happening and are being published all the time. And it's really important to capture that information, assess it, and apply it in diagnostic practice as soon as we can, so that we can provide more diagnoses to more families. So what we have set up is a monthly review session where we share the review of over 20 journals. And as you can see, each month we generally review between 30 and 50 newly published gene disease associations to see whether they can be used in diagnostic practice. So in the first 18 months that we did this, we have added over 340 new gene disease associations that reached green status to the platforms. And it means that variants in those genes can now be reported in diagnostic practice. And over 50% of these are still not in OMIM, so there is a big gap there in terms of that evidence base being used by diagnostic laboratories. The results of this collaboration were published in September in the American Journal of Human Genetics, and this slide is also my acknowledgement to the huge number of people that have contributed to this effort on both sides. What's next for us is that we're depositing our gene curations to the Gene Curation Coalition website, and we hope that this effort will be expanded much more broadly internationally in the future. And Marina is going to talk a little bit more about that next.
Thank you, Zenitsa, and a perfect segue over to Marina. Marina is based at both Geisinger and the Broad Institute and is the Senior Biocurator for the ClinGen resource. So over to you, Marina.
Great, thanks, Lee. So I'm going to give everyone an update on the Gene Curation Coalition and the website that we've had launched in the last year. The Gene Curation Coalition was formed in approximately 2018, and here are some of our the the bottom consists of gene disease resources, evidence resources, with clinical testing labs too. So when we got together, we first wanted to understand the approaches and classification systems so we could really start to harmonize our efforts. And after this was understood, we really worked together to develop consistent terminology, first for validity assessment, but also for inheritance, allelic requirement, and mechanism, in order to be able to post gene curations from a group willing to share with the public. So our database, like a ClinVar, but for gene curations. We're now using this database to resolve differences and collaborate on gene curation projects. So in order to standardize our modified Delphi survey, so you can select some of the original terms that were used by some of the original GenCC members. And so in order to harmonize our terms, we performed 3 rounds of survey, where we first surveyed GenCC members, then an extended including curators of GenCC, and eventually the international genetics community. We came up with these harmonized terms here on the right, and use those to display the GenCC. GenCC itself, search.thegencc.org, was launched as a beta version in December 2020. And this is just a screenshot of our current summary statistics. As of right now, a little bit over 15,000 unique curations submitted on about 100 or so genes from 12 different submitters. Classification strengths at this point, and these are all mapped to our standardized terms that we used that came from the Delphi survey. So as we launched this site, we really wanted to be able to analyze to assess our concordance and begin collaborations to solve differences. These are some of the use statistics. This is a map as of September of the use of the website, the top handful of countries and listed by the number of users. So as of September, we had 200. We do encourage for email alerts if you'd like.
Marina, we're having a little, you're breaking up a little bit in your sound. As just it might be your AirPods. So give that a try, and I'll do you a sound check. Can't hear you at all now.
No, we can't hear you, Marina. There we go. Yeah, okay. There it is.
Okay, sorry about that. So we encourage everyone to go to the website to sign up for email alerts if you'd like to hear about new feature enhancements or changes to the website. And as of September, we had about 36,000 website views by about 4,100 or so users, and at least 100 file downloads of our gene disease curations. As of right now, the entire data set is under a Fort Lauderdale agreement. We're working to finish up the marker paper and hopefully submit by December. But we ask that people do not perform global analysis on the data set until this flagship paper is published. And now I'm going to show you some screenshots of the database. This is the gene list landing page here. So it includes the entire list of all the genes. And along the top, you can filter by different things. So you can filter by HGNC gene symbol by searching a gene. You can filter by submitted disease. You can filter by a particular submitter. And all along the top are the harmonized clinical validity terms that you can check or uncheck if you'd like to only see definitive genes, for example. We also have some frequently asked questions and help buttons along the top to, for example, show you the harmonized definitions for these clinical validity terms. Each row is expandable. So this is just an example here of an expanded row, where if you hit the little arrows here to expand, you can see all of the submitters, what they've classified for a particular disease. And you see little summary statistics across here too. If you click the details button, you'll go to the gene specific page. And there are a couple different tabs within the gene specific page. The first one displays them by classification, with the stronger clinical validities being listed at the top. You'll see the clinical validity here, the HGNC ID, the disease, which I'll talk about a little more in a second, the mode of inheritance with a little info button for each abbreviation, when it was evaluated at the top and when it was submitted, and who the submitter was. There are link outs to public reports, for example, if this is ClinGen or Panel App Australia that have public reports of their gene disease relationships. There's also link outs to assertion criteria, much like in ClinVar, if you'd like to see how an effort classifies gene disease relationships. And if you click the more details section, you'll see a submitter specific version of that particular entry. The second tab is by disease. So I want to mention that we use monarch disease ontology as the mapping ontology. The reason that we use this is because monarch harmonizes and includes OMIM and ORFA IDs along with Mondo IDs. And so this allows for the best flexibility for all of the submitters. So we accept all of these IDs, but we use the monarch disease ontology as the overall mapping ontology. If you click the more details button for a particular submitter, you'll get to an individual submission page, which will often have evidence notes or PubMed IDs or a link out to the public report for that particular submission. And there are also individual submitter pages that have the website for that particular resource, a description of that particular resource, and the contact person for that particular resource. If you had any questions about any of their submissions, you could easily reach out and contact that coordinator for that particular site, along with their assertion criteria and a summary of all of their classifications. So we're hoping to get an API in the future to be able to access this data, but right now we have a data download in a variety of different formats available. And for our future work, we're hoping to resolve discrepancies, but also we'd like to build in the flexibility of disease search. So an ontology search and a panel builder. So first, users would be able to search by any term in the Mondo hierarchy, HPO phenotypes, or disease name keywords, and then filter by clinical validity or by submitter, however you'd like, and then download this filter list and use this for panel test design or indication-based analysis of exomes or genomes. And with that, I'd like to acknowledge all of the GenCC members and submitters and those who worked on the website. And I just wanted to spend, oops, I guess they moved it. I was going to mention the Curating the Clinical Genome Conference, but if that is somewhere else in the slide deck, I'll stop there.
Great, thanks very much, Maureen. And I'll ask both you and Zenitsa to join me. And I'd like everyone to be, if you've got questions, to please enter them in Slido. But as you go to your Slidos, I've got a few questions for our speakers. And Zenitsa, I'm going to start with you. And first thing I wanted to pick up was that you commented that the concordance now between Genomics England and Panel App Australia was 85% after there'd been disconcordance had been resolved. What about that other 15%? I mean, are they genes that are in doubt?
Well, we've reviewed them very carefully, and we're happy with the ones that are left. Quite a very big proportion comes to the definition of the severity of intellectual disability. So I think Genomics in England apply a higher threshold for example, not including causes of mild intellectual disability on that panel. So that's the biggest source of discrepancy. And then the other big source of discrepancy is the borderline family gene disease associations between amber and green. And for example, how we weight functional evidence or really good quality functional evidence to, for example, get it over the line. So we in Australia, I think, have been a bit more permissive than Genomics England curation team.
Right, thank you. So a question for both Marina and Zenitsa. Aren't GenCC and Panel App implementing the same concept? Who wants to tackle that one?
It's a really good question, and it's a bit of a subtlety. So I think that, and correct me if I'm wrong, Zornitsa, but I think that Panel App, really the question is, does a gene have enough evidence to go on a particular panel for a particular disease? Whereas for the Gene Curation Coalition, it's really, does this gene have a relationship to any particular disease? So it's not necessarily so much, should this gene go on a panel? However, we think that the evidence for Panel App and Genomics England is very, very valuable. And so it's just a little bit of a subtlety that other submitters to the Gene Curation Coalition aren't necessarily asking the same question. So we're really just trying to aggregate evidence for gene disease relationships at the GenCC level. And pulling in this Panel App data is very helpful for us, but it's just a little bit of a subtle difference there.
Any additional comments, Anitza?
No, I think we're just coming to the same problem from slightly different angles, as Marina said, in slightly different use cases, but obviously gene disease relationships very much underpin the decisions about which genes go on which panels.
And I think also from the Panel App perspective, the organisation related to a particular clinical presentation, so that there's a hierarchy of prioritising. If you've got a presentation with mental retardation or epilepsy, the particular panel of prioritised genes would be different.
So it is very much a resource that's focused on diagnostic use by laboratories.
Excellent. So Zanitza, from a question from Augusto, so it's going to be a hard one. Do you think that there is a need to create standards for what a gene curation event is, and perhaps how different panel repositories share data?
Create standards for what a gene curation event is. I feel a little bit divided about that, Augusto. I think at the moment we would like to amass as much contribution as possible. So I'm not too strict with my submitters, and I appreciate any little piece of information that they provide. But I think when it comes to putting those multiple reviews together and having an overarching conclusion by the curator team, yes, there's definitely a need to have a standard that we follow for that.
So back to you, Marina, with this question. Scaling. I mean, we all rely on ClinGen and ClinVar, but how do you see this going in the future? How do we scale this up so that we're collecting all this data? Can it grow from a one-on-one comparison to many different organizations? And when you that's at the gene level, and then when you think at the variant level as well, it's huge.
Yes, it's really overwhelming to think about sometimes, but I feel like efforts like GHIF and GenCC are trying to work towards that we were able to grow this resource so much faster by combining a bunch of different submitters all together and putting all of our work together than we could ever have done separately. So I think we need to keep working together. And I meant to mention this in my talk, but if any group thinks that they have standardized evidence for gene disease relationships and would like to submit to the GenCC, please go to the website and contact us using the email button, because I feel like we really need to collaborate together to tackle these tough questions.
Yeah, and I think beyond putting them together, there's going to be probably a big requirement for curators that want to then work on discrepancy resolution over the coming years.
Definitely.
Yes.
Because I mean, I guess the dream would be to have, versions of Panel App across many different countries where it was really interesting to see the journal article reviews, and I think it was the addition of 300 new disease genes in a relatively short period of time. So, from that perspective, making this an international effort to contribute to that knowledge base through this consortium, I think is very valuable. And, we even find that within our country, getting different labs to be sharing levels of evidence between the laboratories is also incredibly useful. Sorry, yes, Anitza?
It's very important to have these tools, but because before this we had Excel spreadsheets or worse PDFs, and those are not shareable and not useful nearly in the same way.
No, at all. The next question is just moved up. So given thousands and soon millions of gene and variant curations done in private laboratory companies throughout the world, what connections are anticipated with them? Marina?
I know that I flashed this slide pretty quickly, but actually some of our biggest submitters are private companies right now. Ambry, Illumina, Invitae are all partnered with the GenCC right now. So we really do encourage not only academic institutions, but private laboratories, if they're willing to share, to reach out to us.
And also for you, Marina, how can we benefit from GenCC in cancer research for gene prioritization and novel gene driver discovery?
I think it's twofold. First of all, you can be using hopefully disease-specific search on our website in the future to be looking for genes that are potentially associated with cancer. But then also, I think it might be helpful to look at some of the assertion criteria, how people classify gene-disease relationships. I'm always pointing that out to researchers who are looking for discovery to kind of start to understand the experiments that we need to answer the questions if genes are connected to disease, like animal models, expression experiments, functional alteration experiments. So I think it's twofold, the front end and the back end.
And then final question, there's two that have come up, is around the implementations of panel apps. And it's good to see Augusto sitting there on the screen as well, because it's how would you go about as a new country looking at this and thinking, gosh, I wish we had panel app. How would you go about setting it up in your country? So Zanitza, apart from talking to Augusto, what would you do?
Asking really nicely. It's open source, and I don't want to speak for Oliver, but it wasn't too hard to set it up. It was reasonably straightforward, but there's setting up the software itself, but then populating it is a lot of hard work. And so it depends on how much pre-existing gene curation resources you have that you're able to upload.
Oliver's just made the comment that he can't even protest. And he said it wasn't too hard. But again, so Augusto, can you turn on your mic and perhaps comment on that? Because it would be, it also, as in our discussion around the Gene Curation Consortium, really brings the more instances of panel app we had and their interrelationship with Clinton, the more rapidly we would accumulate all of this evidence.
Yeah, I think, can you hear me?
Yep, sure can.
Yeah, good. I think there's a number of thoughts on that. So the first one is that one of the reasons why different institutions want different panel content is because they might want to lock that content for a specific purpose. That often has to do with compliance and things like that. And so, for example, we have two versions. We have one that we use to serve the NHS and one that we use for, let's say, advancing the curation and evolution of those panels. So if I were a project starting, I would first ask that question, do I need to have my own version of panels? And it could be because of compliance reasons, so you want to be able to point at a specific thing, or because perhaps you have a different way of looking at conditions, and therefore the content that is assigned to a specific panel is different. I think as we develop resources such as GeneCC, what we can do is then actually more retrospectively populate your panels. It's almost like a menu. This is how I see the condition. Maybe I have a very broad way of looking at developmental disorders, and therefore I want to pick and choose 2,000 genes into it, or I'm very interested in a very small diagnostic segment. And then there's questions as to for how long we're gonna use panels. That still seems to be around for a while. So probably didn't give you a straight answer, but those are all considerations I would be thinking about as we plan where you stand up infrastructure. I posted in the chat the panel app repo, which is usable.
And a relevant question, what level of funding or resource does it take to sustain a panel app instance? Zanitza? Takes one Zanitza.
Well, that's an interesting one for us because we haven't really quite sorted it out. So at the moment, we rely on the diagnostic laboratories that use the resource to contribute to the maintenance of the resource. And for us, that's working quite well at the moment because they have the motivation to do it. But I think in an ideal world, there would be a dedicated central curation resource to assist with that. It is a lot of work to maintain it and to have good quality information.
Excellent. So we'll draw to a close there, but I think obviously we all struggle with gene curation. It's something of general major importance to us all. And we have had a number of workshops, particularly around panel app and gene curation. And Lindsay, I might be putting you on the spot, but are there plans for further workshops for people that are interested?
Marina,
yeah.
Marina can answer that one.
Marina, there we go.
So it's the gene.
Sorry, go ahead.
It's the gene curation meeting in June, but maybe you can speak to that.
I can speak a little bit to this. The slide got moved, so we actually have a collaboration meeting every year. ClinGen and Decipher has a Curating the Clinical Genome meeting. It's virtual. It will be June 6th through 8th next year. We actually have workshop proposals open, so if anyone would like to put in a workshop proposal, we can definitely do a gene curation workshop, but there's all kinds of different topics, abstract-based submissions and invited submissions, usually about gene curation, variant curation, etc. So we'll have that slide advertised tomorrow, I think.
And Augusto and Zornitza, if people were interested in looking at adapting panel app within their environment, what's the best way to go about that?
Happy to chat to anyone who's thinking about setting up their own instance, more from a curation, the clinical and diagnostic perspective. And I guess from the technical perspective, Augusto and Oliver are really good people to talk to.
Yeah, and as I note you that Augusto's put the link on the chat, and Oliver's made the comment that in terms of IT resources for panel app, it's absolutely minor, maybe $200 per month at the current scale. That's Australian dollars, which means it's really, really cheap. Okay, we're now going to move to the next session. So if we could go back to the share slide. And this session arose because a number of us, well, I could comment for Australia, is we've certainly been looking at approaches to our data storage. And I know that in Genomics England, there's been some changes over time. We're looking at the Australian perspective of how we're going to tackle this. And so we're going to get three perspectives from Augusto, from Genomics England, from Corey, from the German Human Genome Phenome Archive, and Daniel MacArthur from the Australian perspective, but also from his experience at the Broad. So again, for this session, we'll have the three presentations, and then we'll go and have fun on Slido after that for Q&A. So please add questions to Slido. And Augusto, over to you.
Great. Good morning, good evening, and thank you so much for letting UK have a central mid-afternoon slot. So yes, my name is Augusto Rendon, and I'm delighted to be joined by quite exciting speakers next to me. So let me tell you a little bit about the experience we've had in Genomics England around cloud adoption. When we started about 8 years ago, putting all these tools and platforms on the cloud was not accepted both by governments, but also by individuals, and that has changed a lot. And so one of the things that really did it here in the UK was policy papers put out by various government institutions, but here's a particularly important one by the Department of Health and Social Care, where they set out their vision of how new technologies in healthcare should be delivered, and it's a cloud-first policy. So today in the UK, if you're going to put out some health application, health platform, then you should really consider the cloud first. And that's because they recognized, as we now do after having experienced many years of on-prem, that things like just security and making sure that the platforms are resilient and backups are easily, updates to OSs are easy, and so on and so forth. It's just so much better done by the cloud providers, the big cloud providers. And you have the cloud, which is very large, perhaps not infinite. And we often, depending on which location you're in, you'll run into the lack of infinity of it. or the finite nature of the cloud, but in general is much bigger than what we have. And then the big one is also this elasticity, which is that we don't tend to be very good at predicting our workloads, and therefore trying to say how big is my HPC becomes a whole enterprise. Of course, the cloud is connected and it's native in the internet, and therefore sharing things. And in this particular setting, for them, it was a way of increasing security and having appropriate access. More generally, we talk in GA4GH a lot about federation and interoperability and so on, and that's by default because it's the internet. And then finally, this whole idea that we shouldn't have to look after the whole stack all the way from like hardware to software. The cloud allows you to essentially stop worrying about little things that are perhaps very complicated, such as networking and hardware and storage, and you start to worry much more at a higher level. That lets you move much, much faster. And if you're interested, and once you have the slides, you can just click and read more about that from a department from this present publications. And so that set us in a course to start moving more and more of our systems to the cloud in the last three years. And where we are today is we have moved the majority of our applications to the cloud. We still retain both storage and high performance compute in our data center. So we haven't moved storage yet. We happen to have a lot of it. We have about 60 petabytes times 3 locations. That's primarily genomic data and users data from researchers that are accessing our data. And the way we've done that is by using a technology where you have a very fast hot layer of storage. We only have about 4 petabytes that is connected to then slower but much cheaper storage. And this combination happens to be quite fast, provided that your data sits in the fast layer. Otherwise, it's just as any other object store. And so we haven't moved this to the cloud yet. And we're thinking how that could be done in the cloud, but cost of cloud storage for data that needs to be hot all the time is quite expensive still in comparison. And then we have a legacy HPC, and more we're adding GPUs for deep learning type and machine learning type algorithms. And then we run as a pipeline Dragon, which uses field programmable gate arrays. So we also have a large battery of such servers. And so getting the data close to the compute remains a huge improvement. However, we have the rest on AWS, and that includes both all the systems where we have to serve the genomic medicine service. And so everything from, for example, ordering tests, tracking samples, orchestrating pipelines, providing results or analysis to labs so they can do interpretation, as well as the non-HPC or storage components of our on-prem research environment. And then we have, since a year ago, a year and a half, we've had a cloud-based, completely cloud-native research environment. And we connect those two through a 100 gigabit, what's called a direct connect link. And we're still getting to learn how we can do this hybrid approach. I don't think we're there yet. And indeed, we haven't been able to, for example, at a sufficient level of performance, run workflows from our cloud environment that use data stored on our on-prem in an efficient way. So that's still areas for, let's call it R&D. And I won't go much in detail, but happy to talk about that. So some lessons from that kind of 3-year journey. And so the first one is a bit about a myth. I think when we talk about the cloud, people worry more about the cloud providers, the big vendors. And I think what they really mean is that they worry, particularly in security, that they're worried about the fact that the cloud is connected to the internet, and the internet is a dangerous place. So when people talk about migrating to the cloud and how you develop things, the idea behind it is you should start from a zero trust position. You shouldn't trust that what you're putting in there, so you should treat everything encrypted, lock down the networks, and assume that anything you put in the kind of the open internet will be read right away. If you open a bucket that is not properly protected, even for a few minutes, that data will be scanned and probably used in some nefarious way. So proceed with zero trust. And that's a big change, because as an organization, then you have to start building that into all your training and the way that your developers and your users, not so much the users, but the developers and architects and so on, have to start thinking about how we build applications. There is loads and loads of information about how to move to the cloud. Every major cloud vendor will have very, very detailed best practices for well-architected systems. And so you can find, and they will even often evaluate your own migration plans around security and how it's architected to best use the cloud, how you should have different monitors, how you cost management, and so on and so forth. So follow the guidelines is perhaps my point there. Then a big thing for us, and it's that to get you around the mistrust of cloud providers or other governments wanting to look into your data, particularly for all of us holding sensitive genetic data, is that you should manage the keys to your encryption. So you don't let the cloud providers manage your keys, you manage your keys. That has some implications in how you build systems, but that says that I can tell our participants to say, you know, the cloud vendor, or actually no one else, can look at the data because we hold the encryption keys. And I think that makes a big difference, and it's completely doable. One of the big things we had to do as an organization, we had to create this cloud enablement squad. And what they're doing is they're going and sitting on top of like the raw cloud and building foundations around security perimeters and approaches and best practices, such that other teams can build safely on top of that. So from a kind of establishing your own organizations, that's something one has to consider, setting up a squad really just to build some foundations. I talked about how we haven't really joined up a storage HPC with the cloud, and definitely how storage is more affordable on-prem, but we do have a large team that is looking after storage, making sure we have enough of it, that we're projecting when we need more, and so on. So it is not a complete, what do you call it? You don't look at both the quotes for cloud and on-prem and compare. You need to look at the teams that need to support them and the expertise that is becoming more and more difficult to get. Good. So that was very much like the raw migration of all our systems to the cloud and some lessons. The other big one is about our research environments. And so we have two. The first one we started with essentially is not this like what people have in their home institutions. They would have a large HPC with lots of storage that is attached to it. And our tools tend to be, at least in bioinformatics, a bunch of scripts, some command line tools, and a bunch of applications. And so here's just a little snapshot showing a terminal window. That's how many people are used to. And typically, if we put our code very close to the data, a lot of people will have a repository, of course, these days, like Git. But yeah, it kind of feels like we're used to. Jobs are submitted through a queue, some sort of HPC orchestration system, and you expect the storage kind of just to work if it's Lustre or something like that. And importantly, the way that costs are constrained are because you have a finite amount of compute, and so you're all competing for it, and you kind of know that you cannot go very far beyond it. As a provider like us, it's really nice because, you know, I have 50, 100 machines, and that's all I have. I know how to depreciate that over time, and that's easy. When you're on the cloud, we have observed that users are less familiar with tools required to be on the cloud, and the typical implementation in the research case is that you have this bioinformatics platform, Stera, DNA Nexus. We use one from a company called LiveBit, and so on and so forth. And they sit because between the cloud and the user, because sometimes for a user to just consume cloud services is just a much more a bigger ask. Then there's a switch from like any type of command lines and scripts to starting to settle on a number of workflow languages, Nextflow, WDL, CWL, and so on and so forth. Many of the scripts are actually written in Jupyter notebooks. The use of containers to manage tools becomes very, very important. And many of these applications have things like cohort builders. Then the fact that the code actually is something that you're constantly updating and pulling from the cloud becomes quite important. And together with Docker repositories, which such as Dockstore or Key.io or others, become quite fundamental. And jobs, rather than just sending a command, we start to use APIs and user interfaces, and the storage is a real complication here, because in the cloud you have slow storage, fast storage, directly attached storage, and cold storage, and so you have to think about all of that in terms of optimizing your application and optimizing the costs of your application. So more to think about. I think that the big one here is that actually, if you have money, then, or if someone has money to pay for it, then you can get your stuff done very, very quickly. That you can use different types of compute that wouldn't right away. For example, if you want to run something that needs Spark, such as Hail, then you can just start a Spark system rather than having to configure from scratch a whole Spark system in your space. So while this sounds like a steep learning curve, which is true, the benefits are perhaps quite significant, and we just need to believe that that's true and keep working at it. We, in our case, actually access the data through a remote desktop regardless, and we take the data out through an airlock process. So the data, just for clarity, is not accessible directly from the internet. We still put a remote desktop in front of it. And then my last slide, oops, there we go. It's just some lessons about that bioinformatics on the cloud. The first one, and we've done quite a lot of user research, is that there's a large segment of users that feel quite wary about using the cloud, perhaps for the reasons I was just describing. Lots of learning and lack of familiarity. And so we need to just push more on training. And some starting point around cloud fundamentals, workflow languages, how to build and use containers, how to use Jupyter notebooks effectively will help us get there. There are a number of bodies that are starting to develop standards about what makes a research environment such as these be able to be entrusted with data and to be, say, federated with. And we're calling them here in the UK trusted research environments, and organizations such as NHSX and HDR UK are starting to publish those sorts of standards and certification processes. A big one, at least here in the UK, is that funding agencies and research groups are not thinking about how to pay for research compute in the cloud. So something to think about and continue encouraging people writing grants and also just panels to understand this. Big observation that this is hard to make it work if you want to own a lot of the infrastructure. And so you need to work very closely with the cloud provider, with the platform provider, and then yourselves as to how you make all of this work. Little things about the number of submissions that you can do to a particular batch job, or the type of storage and how it's attached. And it just gets very complicated very quickly. So one needs to think carefully, especially if you're planning to stand up one of these tools inside your own piece of the cloud, rather than just going and adopting a multi-tenant environment. And lastly, I think GA4GH has, of course, many standards for the things I'm talking about here. And it's a great opportunity for us together to lead not only on developing those standards, but driving the adoption, and as part of that, also training in this space. That's all I had to do. Thank you very much to say.
Great, thank you, Augusto. And we'll now, so please, any questions for Augusto, please post in Slido. And we'll now move on to Curley, who works with the German Human Genome Phenome Archive. Over to you, Curley.
Hi, everyone. It's great to be here. I'm today going to talk about German Human Genome Phenome Archive, GA4GH, And I'll do a bit of an introduction because we are a new initiative. In case some of you are not aware of it, I wanted to give a bit of introduction, and I'll talk about how we want to get things started. Let me see. Okay, there's a bit of a lag time. So GHGA is there to be the national leg for EGA in Germany. And it is funded by NFDI, which I will talk a little bit about. And currently we are funded for 5 years. There will be an evaluation, and the idea is to have another 5 years. And we already spent our first year. And there are a lot of participants from Germany. It spans more than 40 PIs and 20 institutions all over Germany. GHG is part of NFDI. NFDI is a new initiative to fund research infrastructures. It stands for National Research Data Infrastructures. And these are so far given topic-wise. So GHG is one of them, but it spans political sciences, economy, physics, and in total there will be 30. There was the first round last year, and GHG was one of them. Now there's new rounds, and some of them GHG is in direct contact with. There is one for microbiota, one for medicine, but those are topic-wise research infrastructure initiatives. Although GHG starts as a national leg for EGA, it actually has a larger scope when it comes to mission. It wants to be the connection between research and clinical care by being the secondary use place for all the data that is produced. And the idea is that will boost discovery, replication, and bring value to genomic medicine, and also will bring these communities that are not touching each other directly, like wet lab scientists, computational biologists, patients, doctors, and other entities that are around this. The two initial research communities that we are targeting are rare disease and cancer. And so most of the PIs that are already part of GHGA consortia are researchers from these two fields. So we have a very strong hold on these two fields. I think one initial question was, why do we need a national leg for EGA? I think one clear answer is the growing number of data sets. The data management becomes an issue, but a bigger problem, at least on the German side, is the regulatory compliance. We are not only subject to GDPR, but also national laws, federal laws, institutional procedures, and there are lots of layers to that. And it is often so frustrating that the data doesn't leave its initial production place. And so I think that one of the major problems that we try to target with GHGA is this regulatory compliance. And that also, is a good reason to have a national leg. And the idea would be that GHGA would be the harmonization center between all these data producing centers like sequencing centers, hospitals, biobanks, and would be the communication partner when it comes to international partners like EGA. There are a lot of entities around GHGA. There are technical infrastructures that are already there, like the bioinformatics cloud. There are new national and international initiatives like plus 1 million genomes or Genome DE that all target bringing genomics closer to medicine. And GHGA will have a key position here by making this data available to researchers for a second use. We have lots of partners, and I think this is more about if it is an HPC or a cloud part. And the major partners in GHGA are the existing sequencing centers. Those are often residing in institutions, and they are either doing or partnering with some compute centers. And these are the main providers of data and data processing. And we are initially partnering with 6 of them in 6 different cities, but we are already expanding this list to more places to have a better coverage. And the idea is that once we start working with a data hub, one of the sequencing compute centers, we layer them with GHGA services. Initially, these services are targeted to fulfill EGA functionality, and those involve storage and archival, but we very quickly want to expand to compute, at least for some proper QC and standardized data processing, at least some alignment, hopefully bringing them to level of variance. And the idea that the thing that we ask for these data hubs to provide is a secure, isolated infrastructure, at least with OpenStack, because we want to use Kubernetes. And we are, again, working with a team of DevOps engineers, both from GHGA side and from this institution sides, to bring that to reality. Second step is to connect them to a central location for harmonization of these services, synchronized user interaction, so users don't need to visit these individual locations, but come to a central location. And then this acts as the node of interaction when it comes to international collaborations, like, as I said, EGA plus 1 million genomes and so on. There are two teams currently we are forming in GHGA. One is the software development team. Those are providing the services. We are focusing on a microservice architecture because the idea for GHGA is to grow further, and that growth should not be disruptive to the process. And we take GA4GH standards to the heart when we are doing the software design. And we are looking at the existing tools, looking at the principles, and whenever available, we want to use these existing tools. Whenever they are not fulfilling the GA4GH standards enough, and we want to build our own. The second team is operations team. That will be the combined centralized teams of DevOps engineers and data stewards, so that they can attack these problems all together. As I said, we want to also harmonize the user interaction. So data stewards, even if they are from different nodes, they will work together to handle all user interactions. The current picture is like this. There are two initial nodes that we are starting with. They are in Heidelberg and Tübingen, and they have their own resources, as I said, for compute, storage, and archival. And on top of that, they also have something nice. There is this national bioinformatics cloud network, network of bioinformatics infrastructure, I think that's the right name, in Germany. And two of their nodes are in, one is in Heidelberg and the other one is Tübingen, and they provide some standardized cloud services. And they already come with some OpenStack that we started using, and we layered it with some Kubernetes and installed some CI/CD pipeline to bring these from GitHub to production. And also the central services are running on a separate instance in the archives at Heidelberg. So this is how we are harmonizing, and I think there are a lot of takeaways from Augusto's talk, and we want to be cloud ready. I think one idea is GHGA to evolve into a cloud. I think the more plausible solution would be partnering with some commercial partners. And there is, I think, a lot of overhead that is not very easy to calculate when you are doing things on your own. And we are, when we are thinking about our services, how we connect to the resources in a compute cloud, a compute environment, we are trying to do it in a way that would be very easy to adapt to a cloud. I think a lot of things that Augusto showed as differences between an HPC and cloud, we are trying to favor the methods on the side of cloud-like ones, so that it will be easier to adopt. The 2021, we spent mostly on hiring and developing concepts and learning, a lot of learning. In 2022, we want to switch to our first production services, and this will be mostly about archival, connecting to EGA, and also for getting these communities up and running for data submission. And going forward, we want to scale out not only by the number of nodes, but also the functionality. We very quickly want to provide some standardized data analysis. I think this will bring a lot of value to the data content. This is what the GHGA team looks like today. We formed a couple of working groups, software development, operations, metadata working groups, data analysis, workflows, project management. As I said, a very, very large part of GHGA is all these ethical, legal concepts and applications, and that is a very big part of GHGA. And we also have an outreach and training team that is just getting started. And we are currently hiring many, many more positions, especially in the technical side for software development and DevOps, that you can check on ghga.de. That's our website, current placeholder website. And yeah. thanks a lot for listening. Happy to take questions on the slide like this.
Great, thanks so much, Corey. We're going to move on to, well, we may have time, we're running a little bit over time. We may have time for questions at the end, but we're now moving to Daniel MacArthur from Australian Genomics and head of the Centre for Population Genomics. And Daniel's going to talk about cloud-based analysis of large-scale human genomic data. So over to you, Daniel.
Thanks very much, Catherine, and good evening, morning and afternoon, everyone. So I'll be, sorry, let me just get this clicking right. Here we are. So I'll be talking today about work that was largely done in my previous position at the Broad Institute, where I oversaw the development of the data sets associated with the EXAC and Nomad projects, which I'll talk about a little bit later. But towards the end of the talk, I'll also mention the work that we're doing here in Australia as part of the Centre for Population Genomics, and also in my capacity as part of the Australian Genomics effort, which Catherine leads. The science that I'm interested in doing has to do with figuring out how we can take advantage of naturally occurring human genetic variation to understand the function of human genes. And of course, this work involves trying to figure out how we can bring together as much data as possible on the distribution of mutations that have occurred in the human genome. And the fact that across the 7.8 billion or so humans across the face of this planet, we have now likely experienced, in most cases, many tens or hundreds of times, every possible single base change that could exist in the human genome that is compatible with life. So the question in the context of human genetics is how we can assemble data from sequenced humans to understand how those variations can impact the function of genes. We don't have exact numbers on how many exomes and genomes have now been sequenced. It's likely somewhere in the vicinity of 10 million or above. And that's, of course, data that's been generated across a wide variety of different enterprises, both in the academic setting, but also increasingly in industry-funded efforts as well as in healthcare. Now, assembling those data into single unified resources of genetic variation would give us huge amounts of valuable data on the distribution of variation across the population and its linkage through to human phenotypes. But there's real challenges associated with aggregating data from multiple different cohorts around the world. So some of those challenges are mundane, like the efforts which have already been referred to a few times, the efforts associated with moving and processing data. That's becoming easier in a world of pervasive cloud computing, a point I'll get back to later, but still remains a significant challenge. There's large issues that I won't get into today associated with ensuring that we can maintain and track the consent and data use permissions associated with individual data sets, often collected over the course of many decades. There are challenges associated with the fact that for many of these data sets, there are the individuals who have generated them or control them are unwilling to share them. And there are also technical issues associated with the fact that different pipelines used by groups around the world differ very slightly in how they process and call variants on those data. And that last point can actually be a real challenge in the context of variant calling data, because that means that if we were to just naively take the outputs of variant calling pipelines that have been run in different places and try to use those outputs to create a single aggregated resource of human variation, that aggregate resource would be dominated by technical differences between pipelines rather than by interesting biological differences. So often there is actually a need to centralize raw data, or at the very least, to figure out a way of making sure that's run through a nicely harmonized pipeline and then ideally jointly analyzed in the process of variant calling. And so that process of centralization and aggregation of data and joint variant calling was something that we spent a lot of time doing in my previous position at the Broad over the course of about 7 or so years, beginning back in 2012, 2013. And this work progressed in 3 waves of data aggregation. In October 2014, we were able to release the Exome Aggregation Consortium, or EXAC dataset. This came from a collection of just over 60,000 human exomes. It took us about 2 years to put this together, and the end result was thanks to a heroic amount of effort from the group, the GA4GH team, what later became the data sciences platform at the Broad, who produced a set of approaches to large-scale processing and variant calling that allowed us to actually look at data at this scale. 2 years later, almost to the day, we were able to release an updated version of this resource, now called the Genome Aggregation Database, or Nomad. And that the first release of that contained just over 120,000 exomes and 15,500 whole human genomes, giving us information about genetic variation in the non-coding bits of the genome as well. And then we were also able to release then the Nomad V3 dataset in October 2019. That contains, this is an update to the whole human genome component of this resource, contains just over 75,000 whole genomes. And that's the current largest release of whole genomes from this resource. Just a few things to say about Nomad before I talk about the lessons from this project for cloud computing. The first is that this was a lot of data to work with. The underlying data was significantly over 10 petabytes of raw FASTQ and CRAM files that we had to process as part of the project. By we here, meaning largely the data sciences platform at the Broad. And across the Nomad V2 and V3 datasets, that's a non-redundant set of just over 200,000 individuals. We did not sequence these data in the Exaca Nomad projects. Instead, we were able to work with consortia based all around the world, but primarily about 90% who had done their sequencing through the Broad Institute. And almost all of whom had done their sequencing studies through case control studies of adult onset complex disorders such as type 2 diabetes, heart disease, and schizophrenia. We wanted to use these resources to build a public data set of the frequency of genetic variants. So we removed as much as possible individuals with severe pediatric disorders. We processed and jointly variant called all that data. And we focused wherever we could on increasing the diversity of the cohorts. So although nearly 60% of the samples in the Nomad V2 dataset are of European ancestry, we still have at least 10,000 individuals apiece from South Asian, Latino, African and African American, and East Asian populations. So not a comprehensive sampling of human diversity, but a reasonable reflection of most of the continental populations living at least in the US. So we, for each of the releases of these datasets, we've made them freely and openly available in aggregate form through an online browser. The most recent version of that's available at nomad.broadinstitute.org. Because of the scale of these datasets and the fact that they're openly available, they're very heavily used. So now deployed as the reference dataset in effectively all clinical genetics pipelines worldwide. The browser's had well over 30 million page views now. We've also, thanks to support from all three of the major cloud providers, we've been able to host the aggregate datasets on both on Google Cloud, on AWS, and also on Azure. And you can actually access all of those datasets through the downloads page on the browser. And that gives you access then to the full list of all of the variants we've identified as part of these projects and the information about their frequency, their functional annotation, and their underlying quality. So why did we need to use the cloud for these projects? We've already talked, and Augusto, I think, gave a fantastically eloquent description of all of the benefits of a cloud approach overall. In our case, the decision was largely driven by necessity, where back in 2014, the existing HPC model that we had relied on up to that point at the Broad Institute was starting to creak at the edges, and it became clear that we probably only had a couple of years before it would be effectively impossible for us to scale HPC growth fast enough to keep up with the growth of sequencing data. And of course, the growth of that sequencing data has only continued to increase over the following years. So this is a plot of the data generated in petabases at the Broad Institute. Here we are back in 2014, where our problem seemed really big. And now we're up at about 40 or so petabases that have been generated to date at the Institute. And then there's separate graphs here showing the numbers of genomes and exomes. So there's now well over 200,000 genomes and nearly 600,000 exomes that have been sequenced there. So as a result of that growth, the Broad Institute instituted a fairly rapid process of migrating all of its production pipelines and most research computing, including all the work done by my group, over to the Google Cloud platform. And that was largely complete by the end of 2015. And then all of the subsequent work we've done in the context of the Nomad resource has been conducted in Google Cloud. And in fact, I think would have been extraordinarily difficult to do in any other computing resource. To be able to execute for Nomad, we were fortunate to be able to work in particularly closely with a group developing the Hail platform for scalable computing. The Hail platform is what we've used, and which runs very smoothly on Google Cloud, is what we used for all of the quality control and analysis pipelines in Nomad. And that was because the precursors to Hail that we would have normally used for quality control and analysis simply broke at Nomad scale. The big challenge for Nomad is that the size of the data, even just the processed VCF, is absolutely enormous. And it's not just that we need to compute against that once, it's that the quality control process is highly iterative and often repeated across the entire data set as we test different models to try to figure out what the best way is to set our thresholds for filtering our variants and determining which ones are actually real. And so that means that if each of those cycles has an extremely long wall clock time, which it would have if we were still dependent on HPC, that would have been fatal for the process. We really had no choice here but to figure out ways of massively parallelizing everything, and that necessitated a move to the cloud. So we worked with the Hail team to develop pipelines built in the Hail Spark-based process for all of the compute-heavy components of our quality control and analysis pipelines. If anyone's interested in redeploying those, the code for our QC and all of our analysis methods is freely available on GitHub, and that's a huge thanks to many people who've contributed to that, but particularly I'll mention Konrad Kuchevsky, Laurent Francioli, and Grace Chiao. We also used Hail for joint genotyping of the Nomad V3 dataset. So this was because we had reached the limits of what was possible then for joint variant calling with the GATK pipeline at around in the tens of thousands of genomes. That simply no longer becomes feasible. And we the Hail team developed a new method for joint calling that actually now scales up into the hundreds of thousands of whole human genomes. We've also been fortunate to be able to work with the Terra team. This is Terra is a cloud-based platform developed by the Broad Institute and built on the Google Cloud, and that provides methods for data and workflow management. I won't have time today to talk about the science we've done as part of the Nomad effort, so I'll just point towards a collection of papers that came out in May 2020 that describe the generation of this resource and various ways we've been able to use that to investigate the distribution of variation across the population. But in moving back to Australia at the end of 2019, I was very interested in figuring out how to address the question of how we can fill in the gaps in the Nomad dataset, and particularly the gaps where communities that are present in large numbers in the Australian population, such as our Indigenous communities, as well as many more recently arrived populations from around the world, are not represented in these large data sets, mostly based on data coming from the US and the UK. And of course, the poor representation of these populations means that rare disease patients from those communities are also more likely to miss out on accurate diagnoses. So in the Centre for Population Genomics, we're focused on using the same cloud-based models that my group previously deployed at the Broad, including Terra and Hail, to build up large data sets of reference variation that are more representative of the Australian population. So we're excited about doing that, and also for the same reason, excited about the opportunity of a process currently underway to define a national plan for genomic data infrastructure across Australia. So very briefly, this arose from a set of a blueprint document that was produced by a government-funded process led by Queensland Genomics. The implementation plan for identifying a way of actually rolling out national infrastructure for genomic management is being led by Australian Genomics, and that will lead to recommendations that go to the federal government next year, hopefully for the large-scale funding of infrastructure to manage this process, spanning not only research data, but also including the interface between research and clinical genomic data as well. We're at the moment in an exciting phase in that process where there's a set of 12 teams currently working to develop prototypes and testing those to explore different ways of managing genomic data within the Australian setting. And I just wanted to briefly mention one. This is the one that my team is most heavily involved in, led by Sarah Kummerfeld at the Garvan, where we're putting together a prototype built around the Terra platform on Google Cloud, and involving a large number of pieces that are that will be familiar, I think, to many people here in the audience. And over the next couple of months, we'll be reprocessing 14,000 human genomes from scratch, 10,000 of those fully localized to Australian data centers, and 4,000 that will be reprocessed in the US and then brought over after that. And that we'll then use that to enable analysis of case control data as well as rare disease family data. I think it's an interesting opportunity to really try out a cloud-based system at significant scale in the Australian setting and make sure that we fully kick the tires on that process. And we're also really excited about being able to work with the other teams involved in that prototyping process. So with that, I'll finish just with a few key messages. Firstly, as Augusto mentioned, the scale of genomic data that continues to increase, but particularly the very spiky pattern of compute, make cloud models really appealing for large-scale genomic analysis. But as multiple people have mentioned in the comments, this is going to require significant changes to funding models and regulatory policies. We've benefited a lot from having well-engineered open source platforms available to smooth the transition over to cloud-based platforms, but it still is a heavy lift in making that adjustment, as Augusto has emphasized. And there are lots of challenges ahead, I think, as we start to figure out how to adopt models that have worked really well in one jurisdiction to the unique local requirements that need to apply to both research and clinical genomics in a variety of settings around the world. So plenty to keep us busy over the coming years, but a very exciting time for cloud-based genomics. With that, I'll finish. Thanks very much for the chance to talk about our work today.
Thanks so much, Daniel, and thanks to all the speakers. We're not going to have time for questions, and there's lots of questions. So what we're going to do is direct them to the speakers for answering in the chat. But I'll now hand over to Mark Caulfield for the next speakers.
So everybody, we're going to look at now enabling clinical data exchange, clinical beacons and cohorts, and it's great to have Jordi Rambler and Laureen Fromont to do this. So over to you guys to talk about clinical data exchange.
Okay, thank you very much for having me here today. Let me check if I can move the slides. Yes, I checked. Okay, so today we are talking about something that has been mentioned in this forum other times, that it's the beacon. It has been mentioned today when we have been asking, you have been asking in Slido about the standards that were implemented from the participants. And beacon is a very simple idea that it's let's share the very shallow thingy just by allowing this type of queries that it's, do you have seen this variant in your data set? And the answer is yes or no. So this is a very shallow thingy that was thought at the beginning of Global Alliance in order to see which is the willingness of and the barriers and so on of the projects and institutions and organizations to really share data that could be seen as sensitive, very, very dangerous thing to share, to have something in internet, as has been mentioned before, and all these kind of things. So at that time, it was said that this is just that social experiment that should move forward in the near future, if successful, to something much more useful or more useful for the community, for research, for clinical diagnosis, and so on. So without knowing anything about that, we start to get the questions or the requests, let's say, from implementers of solutions, of some of the ones we have seen here that are trying to share genomic data with more or less detailed granularity. And they say how we can use Beacon here in order to be part of a bigger community. And these are what the things we are doing right now. Okay, so we are doing this kind of project, like the clinical variant arc or the collaborative Spanish variant server, or something presented by Augusto and Heidi in one of these forums a couple of years ago or 3 years ago, about what are they doing in the context of their own projects and so on. Okay, and they conclude in that meeting, they conclude that there are two types of ways of sharing or domains of sharing. One is what we call variant databases, knowledge bases that claims things about variants. We have seen examples today about GeneCC, for example, and then case level databases where you describe what are the phenotypes and the clinical conditions of individuals, so which are the whole picture of one individual, one case report that you can use to compare with your own cases. And one example of that would be, for example, the Decipher project. Okay, and these real-world projects try to tackle real-world problems, like the one that BRCA Change is showing here about the overlap between different repositories that has this BRCA gene, and also the fact that many of the variants in these repositories still are not annotated, not reviewed, so kind of unknown in terms of what is the effect of these variants. Okay? The real world issues, meaning we have the scenario where some projects try to share information, knowledge, and in the scenario where there is still room for that, although we are doing big efforts in curation and improving and adding new knowledge to all these things. And then we ran a survey in the Beacon network, a thing run by DNA Stack. And the conclusion of this survey, it's not a super big survey, not super professional, not super scientific, but it's giving us a glimpse of what's happening in the community. So we ask, or they ask actually, what activity are these users doing? And you can see that, to our surprise, that many of the users are not just doing engineering or doing academic research. Most of them, more than half of them, are doing clinical research or diagnosis. And if you look in what they are looking for in a Beacon network, they are looking for variant notation for cases, and some of them for literature, so linking between variants and literature. Okay, so we said, okay, we need to do something. So we gather a team of different projects, the library projects and partners that we have around Beacon, and we try to set up what could be something that is doing this next step, this version V2 that we have mentioned, or has been mentioned already in the conception of the Beacon V1 or the Beacon concept in 2014. So what we conclude was that we need to have something that honors the clinical requirements, and so that we can have a Beacon implementation that is easy to set up, as it was Beacon V1, that it's affordable for clinical settings, and that could be fine-tuned to real-world needs, not trying to compete with any of the resources we have seen so far in this forum today, but with helping them to be easier to discover with less effort by the users. Okay, of course they should be secure enough. We have heard about security today also, and the power of Beacon is crystal clear that was related to having a network. So the benefit of Beacon is not only because you like the Beacon maybe on top of some data that was not available before, but that once you have selected this Beacon, you can integrate this Beacon in a bigger network. So you can just add query to one place, one entry point, let's say, you can have this query solved, answered back by many different places. So all the heterogeneity in these places is kind of reduced, harmonized, if you want, by using a Beacon on top of that. Okay, so we end up with this, let's say, Pullman model that is trying to cover a little bit what is the clinical diagnosis domains with some additional stuff here. I see that some of the slides, the arrows has been moved, but the idea is that we cover here the concepts from genomic variations and their annotations, to which experiment has been run or techniques has been run to go into the site that this is a genomic variation, to the samples taken, especially for cases where we talk about tumor or normal tissues, from the individuals, could be health individuals or relative of the targets of the analysis, and all of them gathered together in data sets or in cohorts when we want to have a high-level description, a statistical description of what's inside this beacon or this cohort. Yeah? So describing which are the distribution of genders and ages, the differences in genotypes and in phenotypes and all these kind of things. And in case of the cohorts, we have based the beacon model largely in the ODC or MOP model for cohorts, and in the case of individuals and biosamples, we have based largely the model in the phenopackets B2 standard also from the Global Alliance. Okay, they are not exact because we would like to allow the beacon models to live independently of the evolution of other standards. So we leverage these standards, we adopt these standards, we allow the user to use the standards, but the minimal thing that beacon is sharing is not exactly the standard, it's something smaller, easier to implement if you want in terms of volume extension than these very powerful standards. Okay. So in terms of course, for example, the idea is, as we said, follow the Odyssey concept of that it's a set of individuals satisfy a set of inclusion or exclusion criteria for a given period of time. And then we have beacon being able to have a response on that with many different levels. So beacon would be able to, is able to respond with a Boolean answer. So you can ask a beacon, do you have females younger than 20 years old that is having hypertension of 15, okay? And then the beacon would be able to say yes, or should be able to say yes, and I have 100 of them, okay? Or and so on. Or if we are talking about cohorts, then they can say, okay, and these are the age distribution, these are the ethnicities or the geographic locations or anything that this cohort is having annotated on it. Yeah. So this idea unfolds in one example of what is the modeling beacon. We have all these different types of subtypes of information inside the cohort model. That is the metadata about the cohort, inclusion criteria, the data usage conditions, the statistics, meaning the distribution I mentioned before, the data types, you have genomics data, you have imaging, you have a lifestyle question or something like that, and the collection events, if this is a longitudinal cohort, then you can say we have collected this thing at that time and so on. And you have on the right side one example of how this looks in a prototype. Okay, you can see that this is not fancy at all. You have for H3 Africa, you see the locations of the individuals in this cohort, the distribution of genders, the distribution of ethnicities, and so on. So it's, as you can see, it's a Pullman thing here, just to illustrate the concept, and that's doable. And this has been done, this example in particular has been done in the context of the Sineca project. Okay. So I showed that already. And we have started to test that. Initially, we discussed that with driver projects, but at the same time, we're getting a request from local institutions. So initially, we have a project with Catalan hospitals near Barcelona or in the Barcelona city, and they start with 6 hospitals. Now they are 15 hospitals enlisted in trying to do clinical diagnosis beacon network in this area for them to share the diagnosis that it has found. So it's, if you want something, the humble version of Genomics England or Australian Genomics or so on, but done in a local way, just for hospitals, people really doing genomics diagnosis in their institutions. Okay, so this is an interesting example of how we can make beacon work, not just for big projects that have funds and technology savvy people and so on, but also for much more humble institutions where there's maybe just one bioinformatician, maybe 2 IT people in the whole hospital. So this is an interesting exercise for us. It's quite fun. Yeah? So when we talk about clouds and so on, this is also very fun. So as we mentioned, beacon is having security, and the security is following the 3 levels that the Global Alliance has suggested some time ago, some years ago, about being public in one site if you want, being registered, meaning that you need to have an account, or being controlled, meaning that you need to have an account and having been granted to access this data. Okay, this is the security model, traditional one, based on user identities following Global Alliance standards and so on, and passports and so on. So beacon V2 is trying to keep the simplicity, the safeness, if you want, the feeling of safeness that you can, if this is a word in English, sorry about that, feeling of safety probably, that the beacon is able to allow very simple queries, like one I mentioned before. So I want to have information about that given individual, provided that you have authorization for doing that, or and get Boolean responses, meaning that you still can do in beacon V2 the very same thing that you do in beacon V1. So telling the beacon, do you have this? And the answer being yes or no. And this can apply to individuals. Do you have individuals like that? Or do you have cohorts like this? Or do you have biosamples taken from, I don't know, neuroblastoma, for example? And the beacon would say, yes, I have it. Okay? And then include some information about how to access the data if this is possible. So you can have these Boolean responses with true or false, or if you are trusting your client in this network, you can provide much richer responses with details about individuals, say in phenopackets, for example, or details about the variants using all the information that you have. In order to implement beacons, you have the typical thing, a website that has been lighted by Michael Valdez mainly some months ago. We have the beacon repositories. We have now beacon divided in two things. So beacon V2 is two sites. One is what we call the beacon framework, and the other one is what we call the beacon model. The beacon framework is just all the elements related to doing requests and getting responses and understanding the metadata of the beacon. So which beacon is that, which filtering terms it understands, which endpoint has been implemented. All this metadata about the beacon is in the framework, and the request and the response formats are in the beacon. So if the request is Boolean and the answer is Boolean, or all these kind of things. And then we have the model, meaning the ones I mentioned about cohorts, individuals, biosamples, and so on. So the beacon now V2 will allow you to light other models. So if you live in the proteomics domain, or the macro metagenomics domain, or the microbiome, or something like that, you will be able to use the beacon framework technology, the concept, and apply it to a different model that your community is wanting to use. And this is the beacon framework. And last but not least, we have documentation about these things. As always, documentation could be better, could be bigger, could be more clear, and so on, but this is significant enough. We have also done one verifier, but it's the first iteration of that, so it's not very comprehensive, but it's allowing the implementers to understand if their implementation is following the specification or not, given the flexibility of the specification. And so it's good that they could test that the responses they are generating, or how they interpret the request, is okay, is according to what has been designed in the specification. And of course, I mentioned the beacon network. The beacon network is trying to extend this at a higher level, an order of magnitude if you want. So this allows you to query one place and then get responses from other places in all the different, in all the domain that I had mentioned before. So having said so, I will thank you for inviting me, and us actually, and I thank our funders and our partners and so on, and happy to take any question if there is time for that.
Thank you very much on behalf of all of us, Jordi, for an excellent talk. We're going to take your questions in the same manner as we did for Daniel, Curley, and Augusto through the chat, if that's okay. And I'm going to move us on to the path to optimization of the use of genomics in healthcare maturity models. And this session will be led by Astrid Vicente, Ricardo Jorge, and Melissa Konopko. Over to you, Astrid, and Melissa, who I believe are speaking.
So good day, everyone. My name is Astrid Vicente. I work at the National Institute of Health, which is called GA4GH as well. So we don't have 3 speakers, we have 2 speakers, myself and Melissa Konopko from Elixir. And what I'll be talking about today will be the work we've been doing in the context of the Beyond 1 Million Genome project on a maturity level model for genomics adoption in healthcare systems. So yes, okay. Yes, so I think most of you, or many of you, will be aware of the Oneplus Million Genome Initiative, which stemmed from a declaration of cooperation among European countries to make 1 million genomes accessible in the European Union by linking the access to existing or future genomic and health data, and having therefore a major impact in terms of sharing for research and clinic practice. So to support the activities of this 1+ million genome initiative, a coordination and support action was established and funded by the European Commission, the Beyond 1 Million Genomes, B1MG. And while it has a number of goals related to setting up guidelines and infrastructures for data sharing, it also is aligned with a major goal objective from the roadmap of the 1+ MG initiative, which is driving adoption of genomics by healthcare system. So one of the work packages is personalized medicine delivery and its scientific and societal impact. And it was in this context that we were thinking about how healthcare systems could adopt genomics, how far along they were, how effectively they're using genomic information, what bottlenecks and challenges they were facing regarding genomics, what would be best practices and common tools that we could share across Europe and globally, and how can we promote the adoption by healthcare systems. And through this reflection, we came upon the idea of using a maturity level model to promote the adoption of genomics by healthcare systems. So a maturity level model typically is a tool, in this case for healthcare systems, to self-evaluate the level of their practices in terms of genomic medicines and do this according to a common matrix. And in general terms, what we did was define a number of domains that were relevant for healthcare systems adoption of genomics, ranging from governance, health economics aspects, data and clinical infrastructure, education, ethical and legal issues. And so for each of the domains we developed indicators for particular practices or issues. And for each of the indicators, we established 5 maturity levels. And these maturity levels ranged from practice that is non-existent or ad hoc to an optimized level in which the practice has been well-defined, adopted by health system, and also dynamic in terms of being adaptable to opportunity, to novel evolutions and novel technologies, for instance, and also supportive of international cooperation. So what we hope with this maturity level model is to promote and facilitate the adoption of genomics by healthcare systems and overall make for a more equitable access of citizens to personalized medicine across Europe and eventually globally. What we did was to develop through literature review first the concept, then we consulted with the 1+ MG working groups, which ranged from ethical issues, infrastructure, guidelines and standards for clinical data and for genomic data, and so on. And then after some brainstorming, we finally came up with a maturity level model framework, a draft. And we wanted to validate it so through a Delphi survey. So what we did was to invite a number of experts, and here it was very important, the choice of experts. We didn't really want to a large number of experts, but we wanted experts that were that had a lot of experience in terms of genomics in healthcare, and also were very fully aware of the challenges faced by healthcare systems, and were leaders of genomics programs either in their own countries or internationally. So we invited 21 high-level experts, 14 completed both rounds, and this was launched in July, and we finalized it by early October with 2 rounds and some accommodation of additional comments. So I hope this will work. This is what the maturity level model, the B1MG maturity level model currently looks like. So it has 8 domains: governance and strategy, investment and economic models, ethics, legislation and policy, public awareness and acceptance, workforce skills, clinical organization, clinical genomics guidelines and infrastructure, and finally data management standards and infrastructure. And here we can see, for instance, for ethics, legislation, and policy, we can open this up. We have a number of subdomains, actually quite a few here, and each of the subdomains may have 1 indicator or more than 1 indicators, and each of the indicators does then have 5 maturity levels. And what healthcare systems then can do is align themselves to each of these maturity levels regarding the particular indicators that have been defined. So if I can go back, I'm not fully sure. Yeah. Oh, there, I hope. Yes. Okay, so this is what the maturity level model is currently looking like. It will be available, freely available for everyone shortly, hopefully. What we're developing now are guidelines for using these maturity level models so that we can actually ask healthcare systems, where are you on your journey? And once they have actually define their maturity level, they can define a path for optimization. So we have defined for these guidelines the steps for using the maturity level model. We've defined 5 steps. The first one is for the ministries of health or any the competent institution that is responsible for healthcare systems, may be national or regional. It needs to identify stakeholders, so a group of multidisciplinary and multi-level experts from the relevant national or region agencies that can respond to a survey with this maturity level model. So the stakeholders will need to complete this self-assessment. They may focus on one of the domains according to expertise, or just fulfill them, all of them, but they have to provide the rationale and justifications for selecting a particular domain, and they will have to do the data analysis and then build consensus so that the country does have one response to the survey that identifies in a 4th step the strengths, the weaknesses, and the requirements for maturity. And what we will do still in the context of the B1MG project is define how to get to an action plan for countries. So we'll develop a roadmap with support of any recommendations, guidelines, and standards coming from the Oneplus MG or others, and provide the countries with that so that they can define their path for optimization. So what we're doing, we still have a little bit of work to do before we can actually make this properly available. So now we want to test this maturity level model in real life settings with a pilot with the national or regional healthcare systems. We have some interest already across Europe, and our goals will be to assess the feasibility of using the model, adjust the guidelines accordingly, and then help countries identify their healthcare gaps and strengths, stimulate the discussion across relevant stakeholders in European health systems so that they can, in fact, develop understand what their gaps and strengths are across Europe, and how they can maybe share best practices to improve, and then address the development of an action plan for progress towards optimization. So this is the point we're at, and now I'll pass over to Melissa Konopto, which will talk about a related development of maturity models. Melissa.
Thank you, Astrid. So you've just heard the about the B1MG maturity model, which covers development within the healthcare sector for sharing genomic data and beyond. But there are actually several maturity models out there within, not specifically the healthcare space, but in other genomic and human data sharing areas. And so here I have some of the examples that we have out there. You can see there is the B1MG one under the idea of healthcare and high level, but it also gets quite technical. There is the one being developed under the Converge project, which is for a federated EGA, which will help your advancement within the federated EGA network. There's also ones being developed under FAIR Plus, which are going to guide you on your advancement within taking either a single data set or your overall data sets and making them more fair. So there are also some of the other ones here, the ones we have bolded, the ones that Elixir is specifically working on. I'm sorry. And we are trying to bring them together to make it very clear when you have the ability to, when you need to approach each one. So all of these are being considered when creating a higher level Elixir human data advancement planning framework. So you would approach this one more if you are looking at this in terms of research, whereas Astrid was talking about the B1MG one, which has more of a healthcare focus, though it does connect to research. You would approach the Elixir one if you were looking more firmly in the research area with then reachback connections to healthcare. And it will give you information on how to advance on a higher level along this, and then would point you backwards to the more detailed models there. So the goal of this maturity model is to create a pathway to support Elixir nodes or countries to reach their own federated human data infrastructure goals at a country level. It's definitely something that could be used if you are not an Elixir node. It would work really for most countries, though the way it is specifically being framed, it would be within the Elixir network. So as I was mentioning before, it is a high-level guide to evaluate and plan overall maturation. And so it's a useful guide, as Astrid was showing on the B1MG one. You can not only choose what level that you're currently at, but what level you would like to be at, and then use the spaces in between there to show exactly the path that you would need to take to arrive. And then you could take that information and put it into a funding application and show quite clearly that there is already a framework that exists and you are working towards advancing in there. It is semi-quantitative and becomes a very clear way to communicate to other countries what your current status is. So you can say, I am at level 3 under this technical area, and another organization would know quite clearly what you can do. And it provides a jumping off point to the more detailed models. And so you have this very high level model, and you can say, okay, I know I want to get from point A to point C here. What is it that I need to do? What are the details that actually take for me to get there? And this model will point out to, for example, the B1MG maturity model or the federated EGA maturity model. And that will give you more guidelines and details on how to get there. The Elixir one is focused on capabilities and business processes. And so as you look at the model, it will say, okay, I want to be able to accomplish this. Where do I need to be? And so it'll be worked in by capabilities. And as I mentioned before, it is going to be used as a detailed guide that would support both planning as well as funding. Sorry, I need to go back there. So the domains are based essentially under the 1+ million genomes infrastructure functionalities. So this is the technical areas broken out by data discoverability, data reception, storage and interfaces, data access management tools and processing. But there's also several organizational level domains that it is going to cover, including things like governance and funding. And then the indicators that are broken up underneath there are going to have your greater detail in those areas. And so it's going to have things like national capacity or the LC issues that you are going to face under each of these areas. So we are expecting the first draft of this model to be completed by the end of the year. And we are going to work with some countries to make sure it is validated and useful. And we'll also be working directly with the other groups that were creating maturity models, such as the B1MG group, which we are actively involved in anyway, to make sure that they all support each other and can work directly. Back to you, Astrid, for closing here.
Yes, so these are our acknowledgements. We're very thankful to all the people contributed, and very much so to the Delphi experts who participated in the effort, which was a big effort. We realized that, but I think we got very valuable opinions and suggestions from the Delphi experts. So thank you.
Thank you, Astrid, and thank you, Melissa, for excellent talks. We're going to transfer the Slido into the chat so you can catch up, and we'll keep it there tomorrow in case people want to use it. On behalf of Catherine and myself and the Global Alliance for Genomic Health, thank you for joining the GIF forum today. We'll look forward to seeing you same time, same channel tomorrow for another thrilling, gripping installment. And I'd like to thank all our speakers, and in particular, Lindsay Smith and Angela Page, who worked very hard behind the scenes to make this success. Thank you all so much, and we'll see you tomorrow.